All right, let's start a little bit early here. So a couple of things off the top. So I'll be posting after class an online quiz that'll be due before we start class Friday. Okay, just a couple of questions, kind of gauge where we're at with things with confidence intervals. Also, under files and then in-class data. So actually, let me make sure I put it up in this one. Now that I say this, I want to make sure I did it for all these sections because I had some issues with the first section today. Okay, so it's not there. So let me drag and drop this here real quick. Got everything pulled up. There we are. Here it is. So I just uploaded up there. So the original file was this YouTube dislike data, and we'll kind of start with that. It was opening up weird on Macs for some reason. I think it was because it was too large. It had a lot of text in there. So I deleted some stuff out of it. It has a little bit fewer observations. Is this YouTube data set math? So let's just all open that one and all use that one if you're following along. Kind of use the one that has math next to it, because the other one, for whatever reason, I think it's when it gets uploaded to Canvas, it was too large. So then when it gets downloaded, something gets lost and it was all screwed up. So we'll use this one that has math next to it instead. Okay. So I'll open that up. Maybe. There you go. So it should look something like this. You've got some data over here. You've got a known population standard deviation. You can't see this, but if we just widen that, anytime you see those dollar signs, right, that's just it's giving you the date here. So I'm going to zoom in so we can actually see what I'm doing here. Okay. So last class, we started building confidence intervals for where the true population mean was, and we only had a sample mean. So we said we have to walk before we can run. We start with examples where we are given a known population variance or a known population standard deviation, right? If we know one, we can figure out the other one. And so we're going to basically construct confidence intervals in Excel. So if you Google this or try to look up videos on YouTube, there may be things that show you how to do this with something called a confidence.norm built-in function. It's a little bit harder to use, I think, than what I'm about to show you today. Also, it doesn't give you the opportunity to break things down into steps. So it's harder to see like where you might be making an error. And so the way that I'm showing you how to do it is the way that you should approach that Excel homework. I'm not saying you can't use that confidence.norm and do it correctly, but it'll be more difficult. And I'm not going to go through it because it also has some issues for some stuff we'll do later. We won't be able to use the confidence.norm, and we'll have to kind of break things down the way that we're going to do it today. Okay. So the first thing I'm going to do is think about, I want to build 3 different confidence intervals. I want to build a confidence interval for where the true population mean is with 90% confidence, one with 95, and then one with 99. So I'm going to use this. This is like a bunch of YouTube videos and the likes and dislikes, etc. So I'm just going to do this for likes, right? What's the kind of true population mean for likes for these YouTube videos? So 90, 95, and 99 are just my confidence levels. These are almost like labels. We're not really going to use these numbers. I'm just putting in there so we have a reference. What we are going to need are the corresponding alpha values. Okay? So with 90% confidence, if you remember what we said last class, what would my alpha value be there? So alpha is the area outside my interval in decimal form. So what percent will be outside the interval? 10%. In decimal form, 0.1. Or 0.10 if you want to think about that. 95% confidence level, my alpha would be what? Yeah, 0.05, and then 99, 0.01. Okay. So I've got my 3 alpha values. So if we remember what we were doing last class, I can move my water here. So this is the equation we have for our confidence interval. We add our margin of error to get the upper bound, subtract it to get the lower bound. We also said that we know that the standard deviation of my sample means will be the square root of the original variance over my sample size. Okay. Now, I was given the population standard deviation, not the population variance. That's okay. I could still plug that in here and square it to get the variance, right? Or another version of this, if we simplify it a little bit, would be the same, like these are the exact same thing. Right? And because I'm given the standard deviation instead of the variance, it might be a little bit easier to use this to calculate that standard deviation of my sample means. Okay. So, I can calculate my sample mean and my sample size in Excel. So we'll do that first. So I guess I'm going to move these down a little bit so that I can put the sample mean and the sample size up here. Oops. Forgot an I. Okay. So how would I find the sample mean for likes? Well, that's just the built-in average function, gives me the mean. I'll then go over and select this likes variable. So Control Shift or Command Shift on a Mac, hit the down arrow. And then if I hit enter, it'll close the parentheses and send me back up to the top. I can then find my sample size using the built-in count function. Select that likes variable. So Control Shift, Command Shift on a Mac, hit the down arrow and hit enter to close the parenthesis and go back up to the top. All right. So I've got about 12,000 observations. I found that just using that count function. Yeah. So all we're going to do there is use that average function, then go over to the variable that we're trying to find the mean of, which was this likes variable. Hold Control Shift, or if you have Mac Command Shift, hit the down arrow, hit enter. And that should close the parenthesis and send us back up to the top. So that's stuff that we've kind of already done, right? Using that average, using that count function, that gives us the sample mean and our sample size. Okay. Do you want to see that again? Yeah. Mm-hmm. Oh, sample size. So just the count function and just selecting the variable that we were using, which was that YouTube likes. Likes variable. This variable in column D. Yep. Okay, up to this point so far. Okay. So I now have my sample mean, my sample size, a known population standard deviation. The only thing left I need to do is find this Z value, right? So remember what we were doing when we found this Z value, saying, okay, look, I know that if I were to go a certain number of standard deviations above and below my sample mean, the area outside of that range will be my desired alpha. Well, I've got two sides, so there's half of alpha on each side. Okay? So what we were doing last class is once we figured out what our alpha was, we divided it by 2, we looked at that area up in the table and found that corresponding Z value. Okay? We've done this in Excel already, but it might just not quite look the same, right? To find a Z value that's associated with a certain area in our tail, that was just working in reverse or the inverse. Right? So here, I know the area that I want in the lower left tail. It's just alpha divided by 2. So in Excel, I'm going to create a column where I just find the different Z values for different levels of confidence. Okay. So the formula that we were using, the built-in function, was norm.s.inv. All we have to tell it is that area that we want in that left tail, which is simply alpha divided by 2. Okay. Now, the problem with doing it this way is it's going to give me that negative Z value, right? Now, I just want the absolute value because the positive and negative sign, that's already built into my lower upper bound equation, right? The positive will give me my upper bound, the negative gives me my lower. So I just need the value. So if I hit enter here, sure enough, I get negative 1.64. Now, if we look this up in the table, this is the one where we're always in between 1.64 and 1.65. Right? This is the actual, out to several decimals value. We don't have to be limited to 2 decimals. So I want that same value, but right, I want the positive. Right? So I just want to drop the negative sign. So, I guess there's several ways to do this. You could multiply it by -1, I guess, if you wanted to. But one function that we're going to start using a little bit, so I won't usually introduce at this point, is this ABS. So this is just takes the absolute value of whatever's in the parentheses. So it's going to take whatever that norm.s.inv function told me and take the absolute value of it. So we should get the same value, but positive. Okay. Any questions on this before we keep moving? So make sure you've got not just norm.inv, make sure you've got norm.s. So that tells it it's a standard normal distribution. Mm-hmm. And then did you close both the parentheses? So one thing that, is it giving you like a pound sign num error? Yes, if it ever asks you, you probably forgot the parentheses. Yeah, it just so sometimes it just doesn't, if you don't have the parentheses closed, it gets mad. I don't know why. Some functions it gets mad, other functions it'll automatically do it for you without ever giving you a message. I think it's when you use, I think it's if you use one formula, it'll do it for you. But here we're using like two formulas, right? Absolute value and then norm.s.inv. So if we copy this down so that I can figure out how many standard deviations away do I need to go get my 95% confidence score? How many standard deviations away do I need to go to my 99%? Well, if I copy this down, my cell reference will just keep updating alpha, which is exactly what I want it to do, right? There's going to be a new alpha associated with these higher levels of confidence. Okay? So notice here our Z value is getting higher. Right? This was the idea that as I want to say things with higher levels of confidence, if that Z value is getting larger, what's happening to my confidence interval? Well, my margin of error is getting larger, so I'm subtracting a larger amount to that sample mean. So as I say things with higher levels of confidence, the number of standard deviations away I need to go to build my confidence interval gets larger, which means my interval gets wider. Right? So say things with a high level of confidence, I have to give you a wider range of possible values. Okay. So there's an alternative way to finding these Z values, which kind of depends on how you think. A lot of people, I think, would say this way is a little bit easier, but we could also think about, I want to find what I really wanted, right? I found this and I took the absolute value. Well, that's going to be exactly what Z is, right? The absolute value of negative Z is just Z, right? So instead, let's try to find this so we don't have to worry about messing around with the absolute value function. Well, here, the area I want in the upper right tail is alpha over 2. So what would the area to the left of this Z value be? Just 1 minus whatever this area is. Well, this area is alpha over 2. So if I use that norm.s.inv, but I tell it 1 minus alpha over 2, it should give me the same thing I was finding before, right? Because it should give me Z, and before I was finding negative Z, but taking the absolute value. So let's see if I'm lying to you. So norm.s.inv, move this out of the way, 1 minus alpha divided by 2. Now this should give me the exact same thing. Sure enough, it does. Right? So there's two different ways of doing this. You know, neither one is more correct than the other. I think probably this second way, I guess, maybe is theoretically a little bit more like appropriate to do, but it's going to give you the same value. So who cares? As long as you understand that we're going a certain number of standard deviations above and below to get our lower and upper bound, doesn't matter how we find that number of standard deviations. Okay. Any questions on that? Or you want to see something again? Or... So did you make sure you do 1 minus the alpha over 2 there? So that was the difference that we had here. So instead of just alpha over 2, we subtracted alpha over 2 from 1, which should give us that positive Z value. That fix it. Any other questions? Everybody with me up to this point? All right. So, and then once I had that, I just copied that, just dragged it down and copied it. So at this point, I've really got my sample mean. I have everything I need to calculate that standard deviation of my sample means, and now I have the z-value. So now I can find my upper and lower bound. I'm just going to use Excel to be a calculator, right? So I'm just going to use Excel to be a calculator for this simple function where I just have to select 3 different values. Well, I've already got 2 of them. I'm going to calculate this third one up here. So standard deviation of our sample means. I'm going to calculate over here. So it's just going to be that known population standard deviation that was given to me divided by the square root, which is just SQRT. Right? We've used this before. And then I'm taking the square root of my sample size, or n. Okay. So I'm just gonna, this is all like that third step, it's like the intermediate calculation. Right? So we can just kind of see things getting broken down. Okay? So notice here, the standard deviation is pretty large here. But I mean, YouTube likes are large. Our mean was 160,000. We've got some extremely high likes, right? Some videos that are like, go viral, all these things. And so they're really going to pull the mean up. We have a really long right skew distribution if we were to do a histogram for this. So we should have a pretty large variance or standard deviation here, right? So at this point, I've got everything I need to find my upper and my lower bound. So for my lower bound, I'm just going to take my sample mean. So that was what, right here? Subtract the z-value associated with alpha over 2, which I've got right here, and then multiply that by the standard deviation of my sample means, which is up here. So because I had calculated each of these 3 components, at this point, it's just using Excel to be kind of a simple calculator for me, right? Where I can just click on the values that I have stored in these cells. I don't have to worry about rounding things to the second decimal. I can keep it out to whatever decimal it ends at, and we can be a little bit more precise. Okay. Yeah. Oh yeah. So the sample mean, right? We're just finding a mean, so it's just using that average function. Right? Oh. Okay. I was gonna say, I was going back a ways. If I lost you way back then, I felt bad. So we'll just take that known population standard deviation on the data we sampled from, divide it by the square root of our sample size. Now, if we had been given the population variance, probably would make a little more sense to use this version of the formula, but really both of them will give us the same thing. Any other questions? Yep. All right. So if I copy this down so I can get the lower bound for my next 2 levels of confidence, right? I'm building 3 confidence intervals here. If I copy this down, what's going to be a problem? Well, I copied it down way too far, but I'm using blank cells because it's updating those references I had for the mean and the standard deviation of my sample means. Well, those will always be the same. The only thing that's changing when I'm building confidence intervals of different levels of confidence is that z-value, right? Different levels of confidence only impact that alpha. So I want my z-value to update when I'm building the next 2 levels of confidence, but I want to keep using the same sample mean. So I'm going to freeze that cell reference. And the original variance of the data and my sample size haven't changed. So that standard deviation of my sample means, well, I also want to keep using that same value, right? So I'm going to freeze both of those cell references. I'm going to freeze the cell reference for my sample mean and for the standard deviation of my sample mean. But when I drag this down, I'm going to let that z-value kind of update, right? To be the z-value associated with whatever the next level of confidence I want to do is. So I'll hit enter there. When I copy this down, now I've got my 3 lower bounds. Yep, everything basically except for that cell reference for the z-value. Right? I froze every other cell reference other than that z-value cell reference. Okay. So I've got my 3 lower bounds. Now I just need my upper bounds. Right? Well, what's the only thing that's different in my upper bound equation? Instead of subtracting my margin of error, I would add it. Right? So what I'm going to do is highlight this. I'm going to copy it. To get out of the cell, just kind of, this is always a nice trick to like get out of the cell, because if I try to use my arrows, it'll start putting cell references in, So I'll hit enter, and that just gets me out of the cell. I'll go back over here to the upper bound. I'll paste it. Notice I should get the exact same value here. I've got to format them so that they're all the same. Let me see. Yeah, there we go. So we can kind of see that it's the exact same value. I just copy and pasted. And if I do it this way, it doesn't update cell references. So when I go into the cell, copy and then paste as opposed to dragging it, none of the cell references get updated. So now the only thing that I wanted to change for my upper bound was I wanted to add instead of subtract my margin of error. Okay. So I just copied and pasted that formula into the upper bound, and then change my negative to a positive sign because I'm adding to get my upper bound as opposed to subtracting. Then I can drag this down. And now I've got my kind of 3 confidence levels, my upper and lower bounds. I could say that, the average number of YouTube likes is somewhere between 152 and 176,000. So I'm going to go out on a limb and guess at this data set that they were somehow selecting these to be like large videos, like large, what do you want to call it? Not users, but large, I don't know, YouTube pages, right? And so, we could kind of, I don't know what company was dealing with this social media data, but you could look at them and say, well, your average, your true population mean is going to be somewhere in this range with 99% confidence, we could even say. And it's, not the most narrow range of values, but it's not terrible either. Can you show the formula for upper? Yep. So it was literally, I copy and pasted, excuse me, the exact same formula I had for the lower bound. It's just that I changed that negative to a positive sign, right? Because we add our margin of error to get our upper bound, we subtract to get our lower bound. Any other questions here? So if you double click on the cell, it'll show you the formula. So there's 2 ways you can do it. I highlighted it here because it's easier for you guys to see. And then I right clicked and hit copy. Or notice, even if I don't double click on the cell, it shows me the formula up here in this formula bar. Now you might not have this turned on, which is why I was doing it that way, but you could also copy it from up here in that formula bar as well. Then to get out of the cell, so you might be having this issue. If I like move, or let me see, let me get out of the cell. If I try to like use my arrows here, it's not even allowing me to move. So the way to get out of the cell, and if I, maybe I click off here and I accidentally put a cell reference in, the easiest way to get out of a cell once you can see the formula is hit enter. It just takes you out. Okay. Then when you clicked over here, since I copied that, all I did was paste that formula. Then once I pasted it, I went in and changed the positive to a negative sign. Any other questions? Now you could type it in again if you don't want to copy it over, right? You could just, it's probably easy enough. Like let's say I didn't have this. Well, my upper bound equation is the exact same thing. I'm just going to take my sample mean. I'm going to add that z value multiplied by the standard deviation of my sample means, and then go in and freeze everything. Did I put a $sign? No, put a 4. Freeze everything that isn't the z value cell reference. You could have done it that way as well. That's easier. Yep. Any other questions? We keep moving here. Okay. So we'll revisit Excel at the very end of class. I'll show you one more thing with that data set, but for now, we'll kind of dive into the next thing we're going to talk about, which is the population proportion. Okay. So remember, we had talked about the distribution of sample proportions, which was that they were going to be centered around wherever that true population proportion was. Okay, so that was their mean. We also had an equation for the standard deviation of our sample proportions. It looks something like this. Right? And so the problem was that that standard deviation of our sample proportion required us to know what the population proportion was in order to know that standard deviation. if we're building confidence intervals for a true population proportion, and all we have is our sample proportion, right? Well, the whole reason I'm building confidence intervals is because I don't know that population proportion. So what we're going to have to do is estimate it with the best estimate we have, which is that sample proportion. So to get the standard deviation for sample proportions, we'll replace the population proportion with our sample. It's the best estimate that we have. And we'll be a little bit off. It's going to be an approximation, but it's very close. So it's out to several decimals that it will be off at. So we're not very worried about it, as long as we have a sample size over 30. So we can do a confidence interval for that population proportion, just like we did for the population mean. So I think I'll try to give a little bit of insight to maybe make this a little bit clear. So our confidence interval equation for our sample mean looks something like this, right? And we knew the standard deviation of our sample means is equal to this guy. Okay. So our sample proportions, this was our confidence interval for a population mean. So we built it around our sample mean. Well, if I want to build a confidence interval for a population proportion, I'm going to build it around my sample proportion, right? So it's just whatever sample statistic that I have relative to what the population parameter that I'm interested in. And now instead of the mean, I'm interested in the proportion. But we also said that it follows a normal distribution, and if we subtract the mean divided by the standard deviation, that will give us z-value. So we know that we can use that standard normal distribution still, right? So it's just like what we were doing before with sample means. But then if this is the number of standard deviations the way we need to go, what's the actual distance we need to go? Well, the number of standard deviations times what the actual standard deviation is. But now it's not the standard deviation of our sample mean. Now it's the standard deviation of the statistic we're looking at, which is the sample proportion. Okay. And I just had on the slide there, that standard deviation should be equal to this. Okay. So it follows a really similar format. It's just that our standard deviation for sample proportions is a little bit different. Now I could plug this all in at one time if I really wanted to. As I work through these examples, I'll probably break it down and calculate this as an intermediate step. But if you really wanted to, right, you could do this all at one time, just substituting that formula. So it follows a really similar format. We're going to look the z-values up the same way. It's actually with proportions almost easier in a sense, because I really only have the sample proportion and the sample size to plug in, and then look up the z-value. Before I had sample mean, sample size, population variance, and I had to look at the z-value. So it's going to be maybe fewer moving parts. Okay. Excuse me. I think I want to mention something else at this point too. I'll hold off. I'll hold off on that. I've got an idea. So don't worry about this. This is just something that we need to make sure that our sample size is large enough relative to what the underlying proportion is. I won't give you an example where we have to worry about this, but just to kind of be complete. And then we have our confidence interval equation. So the way I have it on the slide, I took out that intermediate step, right? I wrote it out like this, but you can do it this way as well. So I'll show you how we do it if we were to kind of include that intermediate step. So we can also now start referring to this as the margin of error without being technically incorrect. I said the sample mean, you're not technically supposed to call what we add and subtract the margin of error, but we wanted a name and to be consistent across the examples we'll use. For the proportions, it is actually kind of referenced outside of this class as the margin of error. Okay. So let's look at an example. So there was a poll back in 2012 in Indiana of whether or not people had favorable views of the Affordable Health Care Act. And actually, more specifically, they asked them if they were in favor of its requirement for companies to cover pre-existing conditions. Okay. So what would the 99% confidence interval be for the true population proportion of people who wanted healthcare companies to cover pre-existing conditions? Well, we had a sample size of, we asked 81 people. Our sample proportion, remember, what was the definition of our sample proportion? It was the number of successes out of the number of trials, or kind of observations. Well, here, 63 out of 81 people had a favorable view of this. And so our sample proportion would be 63 over 81, where I think that simplifies down to 7/9. We also have a 99% confidence interval. So what should our value for alpha be? 99%, there will be 1% outside the interval in decimal form, 0.01. Questions on the setup so far? The number of trials, or you can think about this, your observations, or like their sample size. Yep. So this was our confidence interval equation, where the standard deviation of our sample proportions is equal to this. So just putting this up for reference, right? You already have this in your notes, you don't have to write it again. So we can plug in our sample proportion. We can plug in our sample size. The only thing we really need to look up is this Z value. So our alpha is 0.01. So we want to go a certain number of standard deviations above and below, such that the probability of seeing something outside of that is whatever our alpha is, right? 0.01. So that means that half of alpha is on each side. So 0.01 divided by 2, 0.005. Okay. Well, now we know the area in the tail that we want. We're going to look that up in our standard normal or a Z table. Okay. So we go to that Z table. We look up 0.005. So I'm scrolling down. Looks like I'm in between these two values here. So negative 2.57 and negative 2.58. We'll take the higher and absolute value of the two and use that negative 2.58. Okay. So that was just using the table, working in the inverse, which means that we know that this, it's the same value, but positive over here on this side. Well, now I've got the Z value I need. Now it's just a matter of plugging those three values in. Okay. So if I go back to the slides here, I believe got this broke down. So we identified the three pieces of information we needed. We looked up that Z value that gave us alpha over 2 on either side of our interval. Here I calculated the intermediate step here. So I plugged in that 7/9 as my sample proportion, 1 minus 7/9, and then divided by that sample size of 81. So now I've got the standard deviation of my sample proportions. I can plug that value in. I can plug in my sample proportion. I've got that Z value. So here, just a matter of plugging everything into that equation and doing a little bit of computation. Any questions on any of the steps or the procedure or the process, or just in general questions about this? So how do we use this confidence interval? So it's about 0.66 to about 0.9. So I'm just going to plot that on like a number line. So what this is telling me is that the true proportion of people who had favorable views of this was somewhere in this range. If I'm a policymaker, why do I really like this confidence interval? At the very lowest, the true proportion of people who are in favor of this is 2/3 of people. That is wild to get 2/3 of the country behind the same policy, right? So, if I'm looking at this confidence interval and I'm thinking about, can we get this law or whatever pushed through, or have the general public be in support of it? Well, here, the true population proportion of people who are going to be in favor of healthcare coverage that covers pre-existing conditions is somewhere between like 2/3 and 90%. That's really high, right? So if someone says, the majority of the country doesn't favor this, well, the majority would be anything over 0.5. I can tell them, well, it's going to be way more than 0.5, right? It's going to be somewhere between 0.66 and 0.9. So we can start to use these confidence intervals to, rule out certain values, or to predict what the, not necessarily predict, just to make more optimal decisions moving forward. right? So this is, doesn't seem, I guess, too crazy. I think what we're about to do next, we'll see that we can use these confidence intervals in an even more powerful way, okay? But for now, this is the kind of idea. We can build this confidence interval. The true proportion has to be somewhere in this range of values. So the next example I have, kind of going with this political theme, is, I don't know, 2020 and 2016 were fun to teach this class because like it was just, I don't know, everyone, you were seeing it all over the media. Every news organization puts out what polling numbers are. And so you can think about actually being able to predict the outcome of elections before they even occur if you've got a sample, right? So I actually did this back in 2016. This was, I believe, Fox News was the one I used here. So it was like with the most biased sample I could find, or at least that would have predicted that Trump would win. And so we could try to kind of see whether or not we could predict who was going to win the upcoming election. So there's a survey of 912 people. So we can already start thinking about, all right, how am I going to build this confidence interval? Well, I've got 912 as my sample size. The proportion of people who said they were going to vote for Clinton in this 912 people was 46%, or a sample proportion of 0.46. If I wanted to build a 90% confidence interval, what would my alpha value be? 0.1 or 0.10, however you want to think about it. And so I can actually build the confidence interval for the true proportion of people who are going to vote for Clinton. Right? So if I write this down, okay. So all I'm going to do is plug in my sample proportion. Now, if we remember what this is equal to, well, I can plug in my sample size here, plug in my sample proportion. The only thing I really need to look up is that z-value. So the way that we're going to find that z-value is the number of standard deviations above and below that would give us alpha total on each side. If I've got two sides, alpha is 0.1, there would be half of alpha on each side. So 0.1 over 2, or 0.05. Okay. So now I can go to the table, look up that probability of 0.05 and find the corresponding z-value. So I open up that z table, scroll down. Looks like 0.05 is somewhere in between these two values. So negative 1.64 and negative 1.65. So we'll use the higher of the two in absolute value, which is negative 1.65. And then when I'm plugging these in, the negative and the positive sign are already built into my confidence interval equation. So really the toughest part about these confidence intervals is looking up this z-value, right? I mean, the rest of it is just plugging in the information that you're given, right? So 0.46 was my sample proportion, 912 was my sample size. That would give me that standard deviation of my sample proportions. We looked up that z-value, the sample proportion was given to me. So now I just have three values to plug into this equation, and the computation is fairly simple. I mean, this isn't too terrible. So if I do that, I can find the upper and lower bound. Now here, if we only had two candidates, this would allow me to make a prediction, right? Because what would I have to have my upper bound be greater than to predict that this candidate is going to win? There's only two candidates. Yeah, 0.5, right? Well, here, the true proportion of people who are going to vote for Clinton, the highest value is only 0.48. However, we have third-party candidates, so that doesn't necessarily mean anything. So we actually have to go a little bit further. It's going to be a little bit more complicated. But I'm going to write these numbers down so I don't forget them here real quick. So 0.433, excuse me, and 0.487. Right? So we've got the confidence interval for Clinton. We could also do the same thing, but for Trump, right? So the same poll had the sample proportion of people who are going to vote for Trump. So it was 40%, so 0.4 will be our sample proportion. 912 is still our sample size, so we could calculate the standard deviation of the sample proportion of people who are going to vote for Trump. We then plug in our sample proportion of 0.4. we can look up our Z value, but if we want to do a 90% confidence interval, and this is where I'll go back a little bit to show you this slide. Notice when I want the 90% confidence interval, I'm always going to find the same Z value, right? It's the same alpha. It's the same alpha over 2. It's going to be the same exact Z value we find every single time. So I'm going to use that 1.65, just like I did when I was building the confidence interval for Clinton. Oops, I went too far. When I build it for Trump. Okay, so I use that 1.65, plug everything in. I get the upper and lower bound for the proportion of people who are going to vote for Trump. So why this is interesting is we can kind of think about it. And what red? We should make the Republicans red, right? So 0.373 to 0.4 about 7. I'm just plotting that upper and lower bound on a number line. So the true proportion of people who are going to vote for Trump could be anywhere in this range. Right? If we then plotted the upper and lower bound for Clinton, and you have to go back to recall this, but the lower bound was 0.433, the upper bound was 0.487. So the true proportion of people who are going to vote for Clinton is somewhere in this range. So I built both these confidence intervals at the 90% level. So notice they don't quite overlap. So when confidence intervals don't overlap, it allows us usually to make some pretty interesting statements. So notice, even if the population proportion of people who were going to vote for Trump was as high, it was the highest value in our confidence interval, and Clinton's, the true population proportion of the people who were going to vote for Clinton, was the lowest possible value, well, that value is still greater than what it would have been for Trump. So if our intervals don't overlap here, we can actually say this candidate is going to get a higher proportion of the votes than Trump is going to. And, you know, sure enough, she didn't win the election, but she won the popular vote in 2016. And you can use a bunch of survey data from the time, and all of them, you'll get this prediction where you don't have this overlap in the confidence intervals. Does that make sense? Are any questions on that idea? Yeah, it would just take more time, right? You would break it down state by state. You wouldn't necessarily even need counties, right? Because the electoral votes, I mean, for some states, they give out their electoral votes a little weird, so you would have to break some things down. But yeah, you would basically just be doing this like 50 plus times, right? Once for every state, and then a couple more times for the ones that are, you know, have some goofy ways of getting up their electoral votes. But yeah, that's basically what they're doing when they predict the election, right? This is just for the popular vote. It's just that's a little bit easier for an example, right? Yeah, no, they just have plug-in. Yeah, they've got the data. They'll download the data. They already have everything set up, and it'll just spit out the results. What's interesting though, so I can say with 90% confidence that Clinton was going to get more of the vote, right? But what if I wanted to say it with 99? What's going to happen when I want to say things at a high level of confidence? What happens to my intervals? I have to give you more values. They have to get wider, right? And that's kind of seen in Excel. Remember, the Z value was getting higher. So it's probably, if we did the 90% level, it's going to kick out my upper and lower bound, right? It's going to make these intervals wider. And at the 99% level, because they're already so close, I'm sure that if we work the math out, they start to overlap, right? If you do the 99% level, they actually do overlap, and you couldn't actually make a prediction, because if they overlap, well, maybe the proportion of people who are going to vote for Trump is now up here. Maybe the proportion of people who are going to vote for Clinton is down here. So in which case, well, that would predict Trump's going to win, but they also could be here, which that would predict Clinton's going to win. So anytime you don't have it, or sorry, anytime you have an overlap in your confidence intervals, you just can't really say anything. I mean, you just don't know which one's going to be larger. And you don't have to just do this with political data. You could do this with like the proportion of people who own guns for 2 different countries, or the proportion of people who are, you know, whatever your interest is, right? And whatever your groups are. You can compare any group's proportions doing this to see if there's an overlap in the confidence intervals. But I always use political polling data because it's very common. Most people have seen it. Just as another point of reference here, a lot of times when you see this political polling data, they'll be like 40% of people are going to vote for Trump plus or minus 5%. What they're really giving you there, they're just giving you the sample proportion in percentage form. So right, really it would be 0.4. And then this plus minus thing that they tell, or sometimes they'll even call it the margin of error. That's what we're calculating when we add and subtract that. That's our margin of error. That's all they're reporting to you here. They've basically calculated the standard deviation of sample proportions. They figured, they took whatever the Z value was of the level of confidence they're trying to say something at, and they've calculated the margin of error, and that's what they're reporting when they give you those plus minuses. So if you're interested in politics, maybe that was more interesting of an example than some of the examples I've used. I also put up some slides. We're not going to walk through them, but you could do the same thing with the last selection. I think what I ended up doing was I found a poll that was I thought was maybe fairly biased to the left. So I used this one. It was about 1,200 people. You can see the proportion of people who are going to vote for Biden. There was significantly no overlap with Trump's, right? But I then looked at a more biased poll. I think this one's I used Fox News. And here, the proportion of people who are going to vote for Biden just barely overlaps with the proportion of people who are going to vote for Trump. So this is just more examples that you could do this for any election, right? You really could. Yeah, 4 minutes. So I want to show you one more thing before we get out of here that'll set us up for next class. So I've got some Excel files here too for what we did in Excel, just some references. But if we go back to that Excel file we were working off of, one thing I wanted to show you was, how do I find a sample proportion? So here I've got this variable that is whether or not they had more likes than dislikes on the video. Okay? And so I can think about, well, what proportion of videos get more likes than dislikes? Right? So if I've got a 1-0 variable, so let's say I'm flipping a coin, and every time I get heads, I put a 1. Every time I get tails, I put a 0. So I saw heads in the first flip, tails in the second, tails in the third, heads in the fourth, etc. If I find the mean of this variable, I'd just be adding up all the x values and dividing by the number of observations that I had. But if I add up all the x values, what is that essentially telling me? Well, in this case, it would be just 1. Something only gets added when it's a 1 because the zeros don't change anything at all. So if I add up all the x values, what it's really telling me is like the number of coin flips that came up heads or the number of successes over n, which represents our observations. This is literally the definition of our sample proportion. So a sample proportion really is just a sample mean, but a unique case of it where you're finding the sample mean of a 1-0 variable. Okay. And so if I have something in Excel that looks like this, well, how would I find the sample proportion? It's a 1-0 variable. All I'm really doing is just finding the mean. The sample proportion is just a way we identify that we found the sample mean of a 1-0 variable. So we select this more likes than dislikes variable, select the entire column, and I get my sample proportion. It's as easy as that. Yep. So all I'm doing is using that average function and then selecting this variable in column G, which represents the video had more likes than dislikes. That is 1-0 variable. So you can only really find a proportion if the variable is 1 or 0, right? You either see a success or not. So we'll use this sample proportion next class to basically build confidence intervals, just like we did by hand today for proportions. We're going to do that in Excel on Friday. We're also going to then kind of look at, well, what happens when we have a sample mean example, but we don't know the population variance. So I'll be putting up some files on Canvas, like some additional things. I'll explain them all on Friday, and we're going to have some new tables that we use. Other than that, look for that online quiz. So do it before we start class on Friday. The Connect assignment, due at the end of the day, 11:59 on Friday. If you have any questions on that, feel free to reach out. Otherwise, enjoy this nice weather, and I'll see you guys on Friday.